Welcome to the Koch Academy. In this unit, we are studying indices and scientific notation. Today's objective is that you will be able to write numbers in index notation, that you will recognize common powers, and you will be able to factor composite numbers using factor trees. So, let's start off with this opening problem. Which is larger, 3 cubed to the power of 3 or 3 to the power of 3 cubed? And you may want to turn off the video, pause the video for a moment just so that you can try out these problems. So if I was going to do this problem on myself, I would take 3 to the power of 3. Start with this one here. And I would start with the inside of this. 3 to the power of 3 is 3 times 3 times 3. And that to the power of 3. And 3 times 3 times 3 is 27. And 27 to the power of 3. So the next thing we need to do is multiply 27 times 27 times 27. And I'm not going to calculate that out exactly, but it's approximately 19,000 and a bit more. Pretty big number. So let's check it with this one, 3 to the power of 3 cubed. And so with this problem, let's start that over. 3 to the power of 3 cubed. I'll have to evaluate that first. So we get 3 to the power of, now we've already figured out what 3 cubed is. We've done that here. We did that right here with the 27. So we have 3 to the power of 27. Now 3 to the power of 27 is 27 threes multiplied together. And that comes to approximately, it's just under, but approximately 7 billion. So I think we can see that 3 cubed to the power of 3 is definitely a smaller number than 3 to the power of 3 cubed. Okay, so at this point you should be referring to the handout titled Index Notation. And you should see at the top of it an image that looks very much like what we have at the top of this screen. To simplify the product of 3 times 3 times 3 times 3, we can write that as 3 to the power of 4. And this is using what we call index notation. So we call this entire thing the 3 to the power of 4. This is called a power. Where the 4 is called the index, sometimes called the exponent, and the 3 is called the base. And that refers to how many times you should be multiplying, how many 3's you should be multiplying together. So we read that as either 3 to the power of 4 or 3 with index 4. So this one right here is the most common. And if we wanted to express that algebraically, let's say we had a as the base, was written as a to the power of n, where n was some positive integer, meaning 1, 2, 3, 4, 5, could be higher than that, could be 10, could be 20. But we don't know what it is. If I was saying a to the power of n, another way to write that would be with a bunch of a's multiplied together. Here's a, times da 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 da, a, until we have n of them listed here. So what are indices? Indices provide a way of writing numbers in a more convenient form. The word indices is the plural of the word index, and an index is often referred to as a power. So some examples, and you could write these again on your set of notes that goes with this one. 5 times 5 times 5 equals 5 cubed. 2 times 2 times 2 times 2 is 2 to the power of 4. I have 1, 2, 3, 4 2's being multiplied together, and that's expressed right there. And 7 times 7 times 7 times 7 times 7, 7 to the power of 5. Or again, 7 is the base, 5 is the index. And all three of these sets of numbers, 5 cubed, 2 to the 4th, and 7 to the power of 5, are written in what is called index form. We can combine powers, such as here, where I have 5 times 5 times 5 times 2 times 2 times 2 times 2. In other words, there are 3 5's here and 4 2's here being multiplied together. And we have to write that as 5 to the 3rd times 2 to the 4th if we wanted to write that any simpler. We cannot write this any more simply because the 5 and the 2 are different bases. We can only do that if we have the same base. To give you an example of that, if I had 2 times 2 times 2 times 2 times 2 times 2, what do we have there? 6 of those. I could certainly write this one as 2 squared. And this group here, I could write as 2 to the power of 4. And we could see that since we have the same base, both of them being 2's, we could write that as 2 to the power of 6. But for our purposes today, we would actually probably want to go straight to that answer rather than breaking it up. Okay, so how do we use the index form? And at this point, we're switching to page 2 of your packet. So I can take numbers like, I can write numbers like 98 in index form by breaking it down into what are called prime factors. In other words, if I had 2 times 7 squared, I would get 98. Let's just show you how that works. 2 times 7 squared is 2 times 49, and 2 times 49 is 98. And we can also go the other way around. If I have a number that is raised to an index, I could multiply it out to find the integer equivalent of that. And we have a couple of examples here where we have 2 to the power of 5 gets broken up as this, 2 times 2 times 2 times 2 times 2. And I'm just going to group these individually as we go here so that this group here becomes this 4. And then we have the other 3 2's here. Now we're going to multiply these together to get 8. And we've got 2 more 2's. Multiply those two, the 8 and the 2 together to get 16. One final 2 is 32. It's a long way to get there. Sometimes it's a lot easier if you simply memorize that 2 to the 5th equals 32. Similarly, with the 5 to the power of 3, it's written here as 1, 2, 3 5's. We group 2 at a time to get 25 times 5, and multiply that together to get 125. Again, easier to memorize sometimes that 125 is the same as 5 to the power of 3. So a little bit of vocabulary before we move on to the next thing. Prime numbers are numbers that are divisible by 2 unique numbers. In other words, 2 different numbers. One and themselves. And so if you had to think about what was the first prime number, a lot of people might say 1 was the first prime number, but 1 is not, because it is not divisible by 2 different numbers. It's divisible by 1 and 1. In other words, 2 of the same number. So 1 is not prime. The first prime number then is 2, because we can write 2 as 2 times 1. The next one is 3, which we can write as 3 times 1. We don't need to. And I would ask that you pause the video for just a moment so that on your sheet you can write down some prime numbers. And when you turn it back on, you can look at a list and you can check your work. So give it a pause real quick. All right, assuming you've come back, we also have 5, 7, 11, 13, 17, 19, 23, 29, 31, and 37. And I think that's a pretty good list to start off with. Notice that there is one even number. It's the only even prime number. The rest are all odd numbers. Okay, so the next word that I'd like to look at is composite numbers. And composite numbers are numbers that if you multiply them, they're not prime. Basically, they're the opposite of prime numbers. And they are made up of prime numbers. For example, and this would be something good to write down. We know that 4 is a composite number. We can make that up by multiplying 2 times 2, or in other words, 2 squared. 6 is another composite number, and that is 2 times 3. And we can't write that any more simply because we don't have any more than 1 2 or any more than 1 3. After that, we have the number 8. 8 is 2 times 2 times 2, or in other words, 2 to the power of 3. And it starts getting interesting when we get up beyond 10, or maybe a little more interesting. Let's take the number 12. 12 is 2 times 2 times 3. In other words, we could do 4 times 3, or we could do, let me erase that, 2 times 6, and those would get us the number 12. But either way that I break it up into prime numbers, let me write that neater, 2 times 2 times 3, I can write that as a series of prime numbers with indices, 2 squared times 3. Or if I took the number 18, 18 is 2 times 9, which makes it 2 times 3 times 3. We could also write that one with indices as 2 times 3 to the power of 2. So composite numbers can be broken down into what are called prime factors. And one way to do that is to use a factor tree. One of the things that students often ask is there only one way, one set of the prime factors for 12, and is there only one way for the prime factors of 18? And yes, that's true. There's only one set of prime factors that multiplies to give you 12. And factor trees are a nice way to help us do that. So let's take a look at that next. So what I can do when I'm finding prime factors is I do this method with a factor tree. Now these factor trees are already set up for you. You can see that there are little bits. They're already made up for you to fill in. But I'll also show you how to do this without that. So let's say that we're going to multiply these numbers by primes every time. 2, 3, 5, 7, etc. Oh, that was sloppy. And so let's start with the number 40. One way we could multiply out or divide out the 40 is say, well, 40 is 2 times 20. And notice that the 2 is in a circle, indicating that it is a prime number. The 20 ends up in a rectangle. It's a composite. So that means I can break the 20 up more. And so let's take that and say, well, 20 is 2 times 10. I have another prime. I'm going to break up my 10 now to get 2 and 5. And what I've ended now in all of these circles are prime numbers 2, 2, 2, and 5. So I can write that as 2 times 2 times 2 times 5 equals 40, or in index form, 2 to the power of 3 times 5. Now students will often ask me, is that the only way that I could have done that? There is definitely another way. So I'm going to do that again. I'm going to erase what I have here. And I'm going to leave the answer. See if we come up with something different or we have the same. So 40 is also 5 times 8. There's a prime. And 8 we could break up as 2 times 4. There's a prime. And 4 is 2 times 2. And we see the same thing as we have down below. 2 times 2 times 2 times 5. Or 2 cubed times 5. I'm going to do this in a different way without the boxes. So you can see that you don't always have to break it up by primes. For instance, one of the things that occurs to me when I see 40 is 4 times 10. Now none of those are prime numbers. They're actually both composites, so I might think of those as being in a rectangle. And then I can break these down into their primes. 4 is 2 times 2, circle, circle. 10 is 2 times 5, circle, and circle. And again, we get the same answer that we had before. Okay, so I'm going to give you, I'm going to do 54 for you. Again, you might have thought of a different way to do this. I'm going to do it in one way, and then you can try it in a different way if you'd like. 54, if we're breaking it up into primes, as the directions up at the top say to do, I can think of that as 2 times 27. Yeah, 2 times 27. 27 is 3 times 9, and 9 is 3 times 3, which means that we have 2 times 3 times 3 times 3. In index form, it's 2 times 3 to the power of 3. 100, again with primes, 2 times 50. 50 is 2 times 25. 25 is 5 times 5. 2 times 2 times 5 times 5 equals 100. In other words, 2 squared times 5 squared. So on your sheet at the bottom of the sheet, you've got 3 more, 16, 75, and 90. I'd like you to pause the video and try those 3 and turn it back on when you're finished and ready to check your work. Okay, hopefully you've turned it back on. The answer to 16 is 2 times 2 times 2 times 2, or in other words, 2 to the 4th. 75 is 3 times 5 squared, or 3 times 5 times 5. And 90 is 2 times 3 squared times 5. In these boxes, you would have a 2, 2 3s, and 1 5. All right. Okay, next I'd like you to take a look at the table of the common powers. The powers of 2, the powers of 3, powers of 5, and powers of 7. Pause the video one more time and fill those out. When you turn it back on, you can check your work. Okay, so if you're turning it back on now, let's take a look at those powers of 2. And I'm just going to fill in the answers as I go across. It would be 2, 4, 8, 16, 32, and 64 is 2 to the power of 6. For the 3s, 3 to the first is 3, 3 squared 9, 27, 81, and 243. Powers of 5, 5, 25, 125, and 625. Lastly, 7, 7, 49, 343, and 2,401. These are all really good ones to have memorized. It'll make your work go a lot faster if you know that 2 squared is 4, that 3 cubed is 27, that 5 to the power of 2 is 25, and so on. These are all great ones to know. Okay, one more thing that we need to do. We're going to evaluate these powers here using the powers that you have at the top of this page. And you may, again, want to pause it so that you can find these answers here. All right, assume you're turning it back on. If I were to evaluate this, I'd get 9 times 8, which is 72. This next one, 2 squared is 4, times 3 is 3, times 5 squared is 25, and then I multiply that together to get 300. Lastly, 2 to the power of 5 is 32. 32 times 9, and I'm not really sure what that is off the top of my head, so I'm going to multiply that together. 9 times 2 is 18, I'll carry the 1. And 9 times 3 plus 1 is 28, so we get 288. Okay. What's at the bottom of your page here, the questions about negative bases, we will actually pick that up in the next video. So for now, what I'd like you to do to make sure that you're strong in this area is to complete the exercises in your textbook. It's 2A1. It's on page 53, or begins on page 3 in your textbook. And please do numbers 1 through 5 as an assignment to make sure that you are ready to move on to the next section. So, thank you for listening to me on the Koch Academy, and good luck.